Hi folks, welcome back to my channel. This time I come to you with a series of solved examples from welded joints, an extremely important topic for mechanical designers and engineers in particular. So without much ado, let's get started. So here we have a small plate as shown over here, which is welded to this vertical support, and the dimensions are given here in SI units. Now the question I have for you is find the safe bending force F if allowable shear stresses are 140 MPa. So in this video what I'm going to cover is I will start with basics and then we will go ahead how to evaluate the shear stresses in the weld. First things first. So what should be our approach? A well accepted conservative approach is that consider the external loading, whatever external loading you have on the weld joint. Consider that external loading will be carried by shear forces on the throat area of the weld. So you can always ask, what about the normal stresses? Yes, they will be there, but by this approach, we are going to ignore that. By ignoring the normal stress on the throat, the shear stresses are inflated sufficiently to render the model conservative. So this is a conservative approach, but this is an accepted one, so we'll stick to it. Now let's go ahead. So having seen the procedure already, now the next step is drawing the free body diagram of the well group. So it is pretty straightforward because the problem in hand is not that complex. So when you draw the free body diagram of the weld group, so this is the top weld and this is the bottom weld. We had only two welds, that two fillet welds. In fact, these lines represent a rectangle. I will be coming to that later. But for the time being, if you draw the free body diagram, there will be a shear force that will be acting along the y direction, or to be very precise, minus y direction, and it will be acted upon by a torsion or a torsional moment which will be equal to this F times the distance. In fact, I can go over here and explain. The torque is coming because of this distance, this eccentricity. Make sense? Now this is the free body diagram. So these two are the reaction forces and the reaction torque, and this whole thing is in equilibrium with these two reaction forces. So what happens due to this system of forces, there will be certain kind of stresses that will be developed here, but we told that we will consider that this whole external loading will cause only shear stresses. So let's start with the force F. So we know capital F can cause a shear stress that will be equal to, let me call that tau y, because that is going to cause a shear stress in the y direction. That will be F divided by A, where A is the total area, total throat area of the weld group. Makes sense? Pretty straightforward, isn't it? Now, is that enough? No, we have another force. What? So additionally, due to the distance between the weld bead and the location of application of load, an additional moment will be generated which will cause torsion. And we have learned the methodology to evaluate the torsional shear stress when there is a torsion acting on a bar or a rod. This equation we will use, where T is the torsional moment, pretty easy to find that out. Then radial distance from the CG of the weld group to the point of interest. Then J is the second polar moment of area of the weld group. Pretty straightforward for what we have learned in the basic solid mechanics will come handy in this kind of cases. Now here, so this is the weld group. These are the dimensions D and B. So each of these lines in fact represent a rectangle like this, where B is weld throat size. Be very careful about it. It is not weld leg size, but unit weld throat size. So this is an approach. So we will consider that, we will evaluate the inertia properties for unit weld throat size. That's why I put a 1 over here. Now What we have to compute? We have to compute second polar moment of area. Area is in fact straightforward, 2b. Considering this dimension as 1, the total area will be 2b. Now, second polar moment of area about an axis is integral r square dA. dA is the small areas. But another equation to find J, which is the polar moment of area, is that we can add the two orthogonal second moment of areas, which are IXS and IYY. So in this case, I will go back and explain. First, we will evaluate what is IXS. So IXS will be the second moment of area about this axis, which is pretty straightforward because we have two areas over here and they have, using parallax's theorem, assume that I have a parallel axis to x passing through this, its moment of inertia about this axis will be very small because you have a 1 cube coming over here because it will be b1 cube divided by 12. Let's ignore it. But using parallax theorem, what happens? We can take this area times half of, the distance square. This area times the distance squared. Similarly, this area times this distance squared. That will come into play. So considering that, what will happen? Your second moment of area about x axis, that 2 unit second moment of area about x axis will be bd squared by 2. So this is from these two terms are there because we have two areas, one on the top and one on the bottom. This is straightforward, nothing great in this. Now going ahead, now we can evaluate similarly what will be the second moment of area about this axis too, which is your YY axis. Now coming to this area, about this axis it will have bq by 12 because similarly this will also have bq by 12. So to get the resultant one, what you have to do, you have to add both these. Once you add both these, here is your unit second polar moment of area about the axis, which is into the plane, like the z-axis, what we can say. And a torsion is acting also in that plane, the xy plane. So we need to evaluate J about the z-axis. It makes sense. Now what happens? Now, this is a very, very important slide. So we had two things in the free body diagram, one shear force and one moment. So your shear force can cause a shear stress in the y direction as shown over here. Tau y, tau y, tau y. Now your torsional moment can cause a torsion at all these points. I have shown it only at 4 salient points, and those will be perpendicular to the radial distance from the CG. Makes sense? You have a disc under torsion, you have a bar under torsion, you have a circular bar under torsion. Your shear stresses will act tangential. These are all basic things which we learned. So this makes sense. Your shear stress acts tangential as shown over here, as shown over here, as shown over here, and as shown over here. Now, what will be the critical case? Critical case will be here because, and here as well, because you see, you have a component going here, going in this direction here. Now you have the torsional component is aiding it. It will add to it. So maybe you can say tau y plus tau torsion cos theta will be the resultant component acting in this direction. There will be a component tau sin theta here. Make sense? So let me use a different color there. So if we decompose this one, we will have two components. One will be tau torsion cos theta, and this component will be tau torsion sin theta. Okay, so the resultant one will look a bit longer here because we have tau y plus tau torsion cos theta here, and here we have tau torsion sin theta. Make sense? So this is the region where we These two regions are the regions where we expect the shear stresses to be maximum. Now what else? We need to find the resultant shear stress. So what I have given here is, you know, you need to square these two terms together. Then you will get your resultant shear stress. Now we want to equate that resultant shear stress to the allowable shear stress. Rest everything is plug and check. Like, you can start substituting the values, then you arrive at this kind of expressions here. And all, be careful, because this is the force, this is the distance, so this gives the torsional moment, and this gives the radial coordinate of the point of our interest, and this is how we evaluate the total second polar moment of area. Once you get all these things, it's all plug and chug. Let me not go into the details, but I will quickly show you all these things. Once you have everything, what you have to do finally, you have an expression for your shear stress, resultant shear stress, in terms of the external force, and it is given that your allowable shear stress is only 140 newton per mm square. So plugging in that, you can simply evaluate the maximum load is about 6.06 kilonewton. So that's it. So what did we see? We saw the whole procedure, how to draw the free body diagram of the weld group, then how to evaluate the inertia properties of the weld group, then how to evaluate the shear stresses when you have both torsion and shear force acting together, and then how to find out the maximum bending load it can sustain. Thank you. Thanks for watching.